Okay, so in this video I'm going to be talking about the exterior derivative. And so far we have discussed these differential k-forms. And so remember the differential k-forms sort of correspond to the vector spaces that allow us to define our cohomology. So in the very beginning we were talking about the space of C-infinity functions or C-infinity vector fields, and those have now been replaced by our differential k-forms. So in this video we're going to be talking about the exterior derivative, which generalizes the notion of the divergence gradient and curl, which allows to give linear maps between these vector spaces. And at the end, we can put everything together and get a definition for cohomology. Okay, so how does the exterior derivative work? Well, if you have some space, if you have some k-form omega in omega km, so m is just a manifold or some space that we want to compute the topology of. And so it has some expression in this form, expansion, where you have some sum of functions, and then dxi1 to dxik over, and the sum is taken over tuples i1 to ik, where these are distinct indices going from 1 to n. And so remember that this guy will take in some k-dimensional submanifold of your space M, and it'll spit back a number which sort of is a k-dimensional volume of that space. But again, it's not necessarily volume, it's just some sort of linear combination of volume-like things. And so what we want to do is compute some sort of derivative of that. And what most people do is they say, okay, we're going to define this thing d omega, which is going to be this sum. So we take, so for convenience, I'm going to call this sum f sub I dxi, where I is now a multi-index, which is this tuple I1 through ik. And so fi is just fi1 through ik, and dxi is this dxi1 to dxik. And so the way that they define the derivative is you take all the i's again, and then you take the sum, except now you have another index j, which goes from 1 through n, and then you essentially differentiate this coefficient fi in each direction, and then you add on this dxj, wedge dxi, and it's kind of a confusing definition. One thing to note is that because j is, or because the differentials anti-commute, if j is contained in I, then you'll have some copy of dxj over here, and so this term will be 0. So you can also just restrict to the case where j is not in I. And another thing to note is that because this guy has k different differentials, and this one is one more, this will live in the space omega k plus 1 m. So this is a good definition because it actually defines something that you can work with, but in my opinion it's not really satisfactory because I don't think it's at all clear what is going on here. So usually people take this as a definition and then they derive a theorem called Stoke's theorem, which says that if you integrate d omega over some surface omega, then that equals the integral of omega over the boundary. And so what that means is, let's say that we have something like a cylinder, and so the cylinder is going to be omega, and then the two ends are going to be the boundary of omega. And so let's say that omega is a 1 form. So what that means is that you can integrate omega over d omega, and so this will give you some number. And what it says is that the integral of d omega over omega will be equal to the same number. And so we'll talk about like why this is a useful concept topologically. But in my opinion, this is really the important point that we want from this. And we can actually derive the definition from taking this statement. So instead I want to flip this around and take this to be the definition of the exterior derivative and take this to be a theorem. Okay, so in case you find this confusing, let me just sort of show you that this is essentially what we were doing in the first few videos, where we showed that there was something with zero derivative, either the divergence, curl, or gradient, but it didn't come from something before. So the tools we used there were like the fundamental theorem of calculus, or Stoke's theorem, or if you want to call it Green's theorem, and essentially all of those are special cases of this general Stoke's theorem, or what I'm going to be considering the definition of the exterior derivative. So in order to show that, if you have some curve, let's call it gamma, then you have that the integral over gamma of the gradient of some function f is going to be equal to f of b minus f of a. So if you think about it, this is really equal to the integral over the boundary of gamma of f. And so what this means is that it's the sum of f of the endpoints. So the boundary of some curve, or maybe you have some union of curves, is going to be a collection of endpoints. And the fundamental theorem of calculus says that the integral of the gradient of your function over the curve gamma, I guess I should say gradient of f dot dr, is equal to f of b minus f of a. Okay, so let's say now that you have some surface with some boundary, so it may look something like this. And so this is your surface S, and these components correspond to your boundary del S. And so we know that the integral over the boundary of S of f dot dr is equal to the integral of the curl of f dot dn over the interior of the surface S. And this is Stoke's theorem or Green's theorem or whatever you want to call it. And so we're going to reformulate this to say that f is really a one form. And so let's just call it omega. And so what we really have is that the integral over del S of omega is going to be equal to the integral, sorry, this should be the curl, of d omega over the space x, S. And we'll see that this d omega essentially corresponds to the curl of the vector field f. And there's a third case that we have where, let's say that we have some volume v with an enclosed boundary del v. Then the divergence theorem tells us that the integral over del v of f dot dn is going to be equal to the integral over the volume of the divergence of f dv. And so again, this sort of looks like, okay, the integral over the boundary of some quantity is equal to the integral over the interior of the derivative. Over here, again, the integral over the boundary of the quantity is equal to the integral over the interior of the derivative. And here, again, the integral over the boundary of the quantity, which is f, is equal to the integral over the interior of the derivative. So each of these can be sort of viewed as generalizations of the fundamental theorem of calculus, where the fundamental theorem of calculus says that if you integrate the derivative over the interior of the curve, then you evaluate on the endpoints. And sort of if you look at surfaces which look like this sort of actually looks very similar. It says that if you integrate something over this tube-like surface, then that's the same thing as evaluating on the endpoints, which is the boundary. Except that for higher dimensional objects, you can have more complicated boundaries, and so you have a more complicated statement. But all of these essentially fall into this general kind of rule. Okay, so now we want to solve this problem where we are given some omega, which is a k form, and we want to find some k plus 1 form d omega so that this formula is satisfied, where if you integrate d omega over some k plus 1 dimensional manifold omega, then that's the same thing as integrating omega over its boundary. So omega would be an example of the surface with boundary, for example, and sorry, big omega is the surface, and the boundary of that will be these circles. And then d omega would be a 2 form which you would integrate over the surface, and small omega would be 1 form which you would integrate over the boundaries. And you're given small omega, and you want to calculate what d omega would be. And so this is some generalization of the fundamental theorem of calculus, which will allow us to put everything together and actually get topological information out of doing calculus, since it generalizes the tricks we used in the first few videos. Okay, so we'll try proving this in the simplest case through a hand-wavy physicist technique, which is already hard enough that I've messed it up multiple times. But the simplest case is that omega is a one form in R2. And so what that means is that omega is equal to some f of xy dx plus g of xy dy. And so remember what this means is that omega is evaluated on some vector. And here we chose some coordinate system x and y. And so we'll also use these as our basis vectors, ex and ey. And so it's evaluated on some vector of the form aex plus bey. And so when evaluated on that form, you will get the number a times f evaluated at that point plus b times g evaluated at that point. And what you want to get from this is some 2 form d omega. So this will be in omega 2 of R2. And so what that means is that it'll look like some h of x, y, dx, dy. And so you can remember omit the wedge in here, but really it's secretly dx wedge dy. And so again, here you feed in two vectors, and then it spits out h of xy times how much of the multiple of the ex, ey area that pair of vectors generates as a parallelogram. So in order to calculate this, what we can do is we can say, okay, if we have some sort of surface here, then we can split up the surface into a bunch of small little squares and try and evaluate or solve this equation over each of these small squares, and then hopefully we'll get back to the full thing. So I won't prove the theorem because it's not super interesting. I'll give a sketch of it at the end. But I think what's more interesting is sort of getting at the formula of how to get d omega from omega. Okay, so with the setup, let's say that you have a tiny little square here. And so this point here is the point x comma y. This length is, I'll call it delta x. And this length, I'll call it delta y. And then the basis vector in this direction, I'll call ex. Basis vector in this direction, I'll call ey at this point. And then this has a dual basis, dx and dy. So dx evaluates 1 on ex and 0 on ey, and vice versa. So then what we can do is we can just look at the formula and try and evaluate step by step. So what we want to look at is, if you look at the right-hand side, that's saying the integral over omega of d omega. So this is just equal to d omega xy. So I'll use subscripts to denote at what point it's being evaluated. This will be useful in a bit. And you're evaluating this on the two basis vectors, ex and ey. Or actually, I should say delta x ex and delta y ey, because the lengths of these vectors are delta x and delta y. And so if you rewrite that, then that is delta x times delta y times d omega of x comma y evaluated on the vectors ex and ey. Or alternatively, you can think about it as taking a unit square and then evaluating your one form on that. And then because the area of the square is delta x delta y, you're just scaling it by this area. So this is basically how you compute the integral over a surface, because you just split up the surface into a bunch of small squares. But if your surface itself is a small square, then you can sort of approximate by this. And then we'll let delta x and delta y tend to 0 at the end to get an exact formula. Okay, now it's the part which is a bit annoying, which is evaluating the left-hand side of this equation, which is the integral of omega over the boundary of this guy. And so what you need to do here is evaluate omega on essentially each side of the boundary. So if you remember, the boundary of a surface comes with a particular orientation. So if this guy's oriented with ex before ey, then this will sort of be oriented counterclockwise. And so just, you don't need to like worry about the formal orientations. You can just talk about like what you usually know about orientations of boundaries, that this will be oriented this way. And so what will happen is that you have omega at 4 different points. So for instance, this is omega at the point xy. This is omega at the point x plus delta x comma y, and so on and so forth as you go around the square. And you evaluate this guy on this vector, evaluate this guy on this vector, evaluate omega at this point on this vector going left, and evaluate omega on this point at this vector going down. So if you write that all out, the first term is omega xy evaluated on delta ex, delta x ex. The next term is omega x plus delta x comma y, so that's down here, evaluated on the vector delta y ey. So that'll be this vertical vector here, plus omega x plus delta x y plus delta y. So that'll be at this top left point, and then you want to evaluate on this vector down here, which will be minus delta x ex, because this one's going left now because of the orientation, which is counterclockwise, and then plus omega, this one is x and y plus delta y, evaluated on negative delta y ey, because this guy is pointing downwards. And so now what you want to do is set this expression and this whole big expression equal to each other. So what we end up with is that delta x delta y d omega at the point xy, evaluated on the vectors ex comma ey, is equal to, and I'll group these together as w x comma y plus w x plus delta x comma y, no, actually, yeah, y plus delta y. This is evaluated on delta x ex, and this is evaluated on negative delta x ex, and then plus omega x plus delta x y, evaluated on delta y ey, and then plus omega x comma y plus delta y, evaluated on. Okay, so we cut out a bit there, but I basically grouped together the first term and the third term, and the second term and the fourth term. And the reason for that was because both of these are evaluated on EY, and both of these are evaluated on EX. And so what we can do is we can factor some stuff out. So we can rewrite the right-hand side as delta x times omega, I should put negative sign up front, negative omega x plus delta x comma y plus delta y, evaluated on ex. So what I did was I pulled the negative delta x out and then put this up front. I'll put this guy here. Plus omega xy, evaluated on ex. So it may seem strange why I want to put the negative thing first, but it'll make sense in a bit. And then plus delta y times, I want omega x plus delta x comma y, evaluated on ey, and then minus omega x comma y plus delta y, evaluated on ey. Okay. So for this one, I pulled out the negative delta y and put it here, and for this one, I pulled out the delta y and put it here. And so now what you can do is you can say, okay, well, there's a delta x delta y here, so we can divide both sides by delta x delta y, because I mean they're just numbers, they're the lengths of these of the square. And so we get d omega of x comma y is equal to this guy divided by delta x delta y, where you can cancel the delta x's, and here you're dividing by delta x delta y, and so here you can cancel the delta y's. And let's now plug back in this expression for omega in terms of f and g. And I want to sort of emphasize that f and g do depend on the coordinates that you choose, but since we've chosen some specified coordinates x and y, it'll do that. If you don't know about coordinates or don't feel comfortable with them, ignore that comment. But once we do that, we can rewrite this guy as saying, okay, we're evaluating it on ex, so we only need to pay attention to f. So this will be negative f of x plus delta x comma y plus delta y, plus f of x comma y divided by delta y, because that's what's left over in the denominator here, and then plus, now we're evaluating it on ey, which is a second basis vector, so we apply to dy, and dx gives us 0, so we just need to worry about the g's. And so this gives us g of x plus delta x comma y minus g of x comma y plus delta y, and then this is divided by delta x. And So these inputs are just like the points at which it is evaluated, because it's f of x comma y, g of x comma y. And since we're evaluating the basis vectors, we can just ignore the other guy. So now what you can say is, okay, we can sort of Taylor expand these guys. This almost looks like a derivative with respect to y. The one thing that we need to change is put a negative sign out here, and then put parentheses out there. And then if we could change this f of x plus delta x to just an f of x, then we'd be in business, and this would be some derivative with respect to y. But what you can look at is, remember in the end we want to take delta x, delta y to 0, because this is essentially splitting your curve up into a bunch of small squares, and as those squares get smaller and smaller, then your integral becomes more and more exact. So in order to get an exact formula, we can look at f of x plus delta x, comma y plus delta y, and we can see that we can sort of Taylor expand this in the first variable to write this as f of x comma y plus delta y plus delta x times something. And so this will involve like the first derivative with respect to the first variable and so on and so forth. But the point is that what we can do is we can expand this term in terms of second variable and write this as f of x comma y plus delta y partial f partial y at x comma y plus delta y squared times a bunch of garbage plus delta x times a bunch of garbage. And so what we're going to do is, in the end, is take the limit as delta x goes to 0 and delta y goes to 0. So if we look at this expression here, which is this first function, and the second function, we see that f of xy and f of xy cancel. And then when we divide by this small dxy, then these fractions cancel. And what we end up with is a negative partial f partial y x comma y. And then this dy squared gets divided by this dy. And then since we're taking the limit, though, as dy goes to 0 at the end, we can ignore that term. And similarly, this dx doesn't get divided by anything, so this dx lives on, but we're dividing it through, so it's fine. And similarly, this guy almost looks like a derivative, except that we have this y plus delta y here. But by similar approximation, you can just write this as g of x y plus delta y times some garbage. And then because we aren't dividing by delta y, this delta y persists. And because we're taking the limit as delta y goes to 0, we can just ignore that. And what we get is plus the partial derivative of g respect to x of x comma y. And so our final formula is, in this case, if we evaluate d omega at the point x comma y on the vectors ex, ey, then we end up with partial f, negative partial f, partial y, plus partial g, partial x, okay, so moral of the story is, if you take this d omega guy and at the point xy and evaluate it on the two basis vectors ex and ey, then remember, if we write omega as being f of xy dx plus g xy dy, then this guy is going to be equal to negative partial f by partial y evaluated at the point xy plus partial g by partial x, also evaluated at the point xy. Or put another way, we know that d omega looks like some function f of xy, and then dx dy, or again, this is just dx wedge dy. And so put another way, this says that if you feed in the two vectors ex and ey, we know that when you feed that into dx dy, then that'll give you 1. So really, it's saying that this function f is given by negative partial f by partial y, x comma y, plus partial g by partial x, x comma y. Um, and then you can put a dx dy here. So this is the usual formula for at least a one form in R2, that if your one form looks like this, then the gradient will, or the exterior derivative is going to look like that. And maybe you recognize that this looks somewhat like the curl. And to sort of give you an example of uh, a computation involving this, we can consider like the integral of like minus y dx plus x dy, um, and then maybe 1/2, I think, up front. And then, so this guy is going to be your omega. And let's consider this integral over the unit circle S1. So this is going to be equal to the integral over the interior, let's call it d, of this formula applied to this function. So here f is equal to negative y, so we need to take negative of partial negative y dy, and then the g is x, so then we take partial x with respect to x, and then dx dy, and this is going to be equal to, well, this is 1, this is also 1, so it's 2, 1/2, so that you'll just get the integral of d dx dy. So this is like one of the really cool things that you learn in multivariable calculus, that you can compute the integral or like the area of a surface by just knowing information on the boundary. So this is S1, which is equal to the boundary of D. So this is Stokes' theorem in action, and a cool thing that you can try is try and find a three-dimensional analog of this. Okay, so now this is like the simplest case, as I said. This is an omega 1 of R2. Let's try increasing the complexity just a little bit. Let's consider omega 1 of R3. And let's say that we have a little omega in here. So in other words, it's a one form in R3. And so what this will look like is, in general, it'll look like f dx plus g dy plus h dz. And so f, g, and h will all be functions of x, y, and z. So there'll be things which vary across your space. And then you can try and ask, okay, what is d omega going to be? So how can we compute this? Well, last time we knew that d omega, essentially if you compute it on ex and ey, then you're done. Well, in general, remember that we can write two form in terms of like the basis two forms. And because we're looking in three-dimensional space, we know that there's a space of three two forms, which are the three different planes. And so this will look like something dx dy plus something dy dz plus something dx dz. So these are the basis three forms. If you take the basis like orthonormal xyz basis and then the dual basis dx dy and dz. Okay, and then these will be three different functions, f, g, and h. So how can we compute each of these? Well, what we can do is we can do something very similar where we're going to take small squares, except now we have this three-dimensional space here. And so this is the x direction, y direction, z direction. Then the first thing that we can try is we can say, okay, let's evaluate on this square, which is ex and ey. So we can look at what is d omega of ex comma ey. And using the same sort of thing as before, this is essentially the computation that we did earlier, because each of these guys will evaluate to 0 on here because dz applies to 0 on these both vectors, and there's a factor of dz on both of them. So the only contribution you'll get is from f. And we already know that this is this guy up here. So it's equal to f, which is equal to negative partial f by partial y plus partial g by partial z. Sorry, partial x. So then the next thing that you can do is you can say, okay, let's try taking this d omega figure that we have here and evaluate it on maybe this plane, which composes of ey and ez. So you can ask, okay, what is d omega of ey ez? And you will find that, again, I mean, this will only pick up a contribution of this term because the other terms have a dx, but dx evaluates to 0 on both of these vectors. So what you get is a g, and g is going to be partial, let's see here, partial g by partial z, and then partial h by partial y. And then there's a relative negative sign between them, and should look something like this, I'm assuming, but I might have gotten the signs wrong. It might be positive this, negative this. But never mind that. And then d omega of ex ez is equal to h, again for the same reason. And so this is evaluating it on the third plane, which is going to look like this square. So if you evaluate on these two vectors, which will give you that third basis square, then you're going to get h, which is now going to be partial h by partial x, then partial f by partial z, again with the relative negative sign between them. And then these guys, maybe I messed up the signs. It might be plus or minus one of these. So I'll tell you how to get the signs in a moment. But for now, these two guys, how did I get them, or how could you get them? You can do the same exact calculation that we did here. Just evaluate your problem on each of the squares. And then because essentially then you've gotten rid of, for example, if you evaluate it on this square, you've gotten rid of f and h. So then all you need to do is reduce it to a two-dimensional calculation like we did earlier, and you'll get the same sort of thing. So all in all, what that means is that this expression is going to be equal to something like partial g by partial x minus partial f by partial y dx dy plus, let's see if I can get the signs correct, partial h by partial y minus partial g by partial z dy dz plus, let's see what this should be. This should be partial h by partial x minus partial f by partial z dx dz. Okay, so I guess I got this one correct, but this one not correct. So how do I get these signs? Well, it turns out that in general, the signs are determined based on the orientations of the faces. So if you remember, essentially the signs came because we were evaluating this bottom face in this orientation, it's just the orientation of the vector, but then this top face in the opposite orientation. And over here, the left face was in the opposite orientation, while the right face was in the positive orientation. And so based on like which one agrees with the vector and which one doesn't agree with the vector, or in the higher dimensional case, the higher dimensional basis, looking at orientations, then you can figure out what signs these all are. So in general, the rule for orientations is, remember, an orientation of an n-dimensional space is like a choice of basis. So if we look at like a volume element, then an orientation is a choice of basis, and then this induces an orientation on each of the boundary faces by saying what are the two basis vectors, so that if we put the third basis vector first, then that'll result in our interior orientation. So essentially it's saying sort of forget the outward facing vector, and then that'll give you a basis for each of the faces, and that'll be the orientation each of the face. And so that'll give you some sort of a sign which will attribute to the derivatives here. And you can check that what'll happen is you essentially have your omega is of the form sum of fi dxi. And then using the same procedure, essentially you just evaluate d omega on each of the different like one-dimension lower faces. So in R3, what that look like is you start off with a cube, and you have a 2 form which is defined. So let's say that we have something in omega 2 R3, and this is omega, and d omega we know is in omega 3 R3. So you want to start with evaluating d omega on a cube, and then evaluate each of the faces and take differences and whatnot, and then you get some derivatives. And the derivatives work out so that it looks like this. So it'll be the sum over all multi-indices I, and then small indices I, and this will be partial f I by partial xi dxi dxi. So it turns out that if you put the one which you're taking the derivative with respect to up in front, then this will recover the right sign. So over here, for example, since the derivative with respect to y, and we put dy here first, this will have a positive sign, will this have a negative sign. But if you wrote it as dz dy, then it would be switched, which is why the sign doesn't really matter until you like work out what it should be specifically. Yeah, so this works in general. And so for another example, let's say that you have this 2 form omega and omega 2, and you want to find d omega, then omega is going to look like f dx dy plus g dx dz plus h dy dz, and then d omega, following this formula, well, this term will contribute a partial f by partial z dz dx dy plus partial g partial y dy dx dz plus partial h partial x dx dy dz. Now what you should do is take the derivatives of each of these components with each of the different basis vectors. So really you should also get a term that looks like, for example, partial g by partial x dx dx dz. But because this has two dx's, this is equal to 0. And if you don't believe me, just take it as an exercise to try and show that. And take it as another exercise to try and apply this general formula to this expression, and then make sure that you get back this guy. But looking back at this, we can try and figure things out, like combine these terms. And so what we can do is we can take this dz and move it to the end. And every time we swap two of these guys, remember it's something of the exterior, it's locally of the sort of wedge of a vector space. So whenever you swap two vectors, you have to multiply by -1. So if you want to make this into dx, dy, dz, then we have to move dz past two of these guys. So that'll pick up two negative signs, but that doesn't change anything. So this is partial f by partial z. This one, we can also make a dx, dy, dz by moving this over once. So then that'll pick up one negative sign, and that'll be partial g by partial y with a negative sign. And then if we, well, this one's already good. So this one is partial h by partial x. Okay, so I'll have to go through some renaming here to make it look more familiar. But you have this guy dx, dy, dz, and this one's already dx, dy, dz, so that's fine. What I'm going to do is swap around f and h. So make it look like that. I'll do this and f. So this will become h, this will become an f. And so what that does is it changes this to the derivative f with respect to x and the derivative h with respect to z. And then I'll change this from g to negative g. So this will become negative, and so this will become plus partial g partial y. So the reason for that was because now you might recognize these formulas. This guy is the two-dimensional curl. This guy is the three-dimensional curl. This guy is the three-dimensional divergence. If you look at going from omega 0 of Rn to omega 1 of Rn, then what that does is it takes a function f and it sends it to sum of partial f partial xi dxi, just by looking at this formula, because each of these index sets are empty. And so this recovers for you the gradient. So we found the generalization of gradient, curl, and divergence which we wanted. And now we're finally in a position where we can generalize cohomology to arbitrary scenarios like arbitrary dimensions. Okay, so now I want to go through the proof of the actual Stokes theorem, which says that if you have some omega, which is of the form sum fi dxi, this is in omega k of some r to the n, and then you have d omega is equal to this expression, which is a sum over I equals 1 to n, partial fi by partial xi dxi dxi. And again, for normal computation, since repeated terms cancel out, really this is over the set I is not in big I, but that's fine. If you have these two guys, then these always satisfy the relation that the integral over subspace omega of omega is equal to the integral over, or of d omega, equal to the integral over the boundary of omega of omega. So starting with this guy that you know, you can compute this d omega figure, which satisfies this equality always. using this formula. So my proof here was super sketchy because I cut a lot of corners. I said like, oh, ex and ey are constant. If you know stuff about manifolds, then it's like, oh, ex and ey also vary from point to point, so you need to be careful about that. And then you have like these weird things like, I ignore higher order terms, but dx over dy is a weird thing to analyze as they both go to 0. If you want, you can redo the calculations in as much formality as you would like, but I hope I got the spirit across that I want to show that starting from this formula that you want to get to, these derivatives naturally appear. And again, that's by computing sort of the differences of your form evaluated on opposite faces. And I highly recommend you to try out a higher dimensional case or redo one of the cases if you want to understand that better. But the proof of this, or sketch bit, is actually not super interesting. If you care, you can find it in this book. It's a great book, which I recommend to read either ways, but it doesn't quite go through the sort of reasons for why it does the definitions that way, or why the definitions are that way, and sort of jumps into topology right away, which is fine, but I want to sort of explain why this formula is true. But anyways, for the proof is kind of dumb in my opinion. What you do is you have some manifold over here, and then it has some boundary components like this. And so what you do is do your classic tricks of manifold topology, where you just like split this up into a bunch of open sets, and any open set which is away from a boundary component gets sent to Rn, and any open set which is sent to a boundary component or contains a boundary component is set to a subset of Hn, which is the upper half space. So this is inside Rn, but it's the set on which like x0 or x1, I guess, is greater than or equal to 0. And the proof here is you start with your function f, which is defined everywhere, then take some partition of unity with respect to this open cover. And then what you do is you essentially reduce to the cases of Rn, Hn, and computing an explicit integral. So in these cases, d omega, what happens is you integrate over like x2 to xn, and you integrate over x1, and you're integrating d omega, which is going to look like the derivative of some function with respect to x1 plus some other stuff and whatnot. But what you do is, if you're in the first case and it's a subset of Rn, then you're integrating from x1 equals negative infinity to infinity. And because you chose a partition of unity, this f is going to be compactly supported, because the way the partition of unity works is you take your original function, multiply it by the partition of unity, which has compact support, and then use that to change the domain to Rn. But then because the function has compact support, f, or the local expression for f, also has compact support. Or I guess this should be like, I guess f phi I, where f is equal to sum of f phi I, and phi I is a partition of unity. I don't want to go too much into this theory right now. Maybe I'll talk about it later. But yeah, so this guy is compactly supported, and so if you take the integral of this, then this is just f times phi I evaluated from minus infinity to infinity, and this is 0, because as you approach negative infinity or infinity, this partition of unity approaches 0. And then in the other case, in Hn, then you're integrating from x1 equals 0 to infinity, and it's the same sort of thing. You get f times phi I, but from 0 to infinity, and then in the upper limit you get 0. And then in the lower limit, you just get f. And then what ends up happening is that you essentially pick up contributions from everything on the boundary. And I guess to check the details, there's a bunch of stuff to check. But I mean, the proof isn't super enlightening that this thing works. I think what's more interesting to see is how one ends up at this formula in the first place.